So we just reminded ourselves of the examples and definition of strong and weak acids, how much they ionize. But we also want to think about this and be ready to apply it to the Bronsted-Lowry definition. The idea that things can donate, things can accept, but we also turn those into a conjugate, in this case base, or in the terms of a base, into an acid that has the ability to do the opposite. So with our strong acids, any of our six, we would write it as a one-way arrow in terms of ionization, and we would turn into products and mostly or totally stay as products. Our weak acids would turn into products, some would turn back, and we'd have a significant amount of both, and probably more of our unionized acid than the ions they produce. This comes to the strength of the attraction between them and other trends and patterns, which we'll look at here in the notes. But what's important also is to be able to understand how this impacts the strength of the base that they turn into. So each acid turns into a conjugate base, and sometimes the phrasing on this is oversimplified. I'm going to avoid the incorrect phrasing, so it's not even in our heads, but it's phrased incorrectly in a way that provides some misconceptions. So when we think about a conjugate base, we're thinking about how well can the reaction go backwards, or how good is the Cl, the F, or the Cn minus at accepting a hydrogen and turning back into the unionized form. For strong acids, they go to the right 100%. It's very favorable to break apart. That means that this can't go backwards very well at all. It isn't good at accepting a hydrogen, or that chloride or any of the anions of a strong acid are very, very, very bad at being a base or an extremely weak conjugate base. The HF is a weak acid. It turns into F minus, but that does go backwards. So this weak acid makes a conjugate base that is also weak. It doesn't go back 100%, so we can't say that it's strong. We have a weak acid and a weak conjugate base. This acid, and we know this by bond strength in Ka, which we'll get into, but this is an even weaker acid. So it ionizes less, meaning that this Cn is even better at turning back, or the reverse reaction is more favorable than the forward. So the weaker my acid, the stronger my conjugate base is. That doesn't mean that this is a strong base, because I still have an equilibrium. So sometimes we use this wrong idea that, oh, since this is so weak, this must be strong. But anytime it's in equilibrium, both parts are weak, but we can say that they're stronger or weaker or more or less favorable. So some phrases that are good is that for our strong acids and bases, their conjugates are so weak that they do not go backwards at all, or they are negligible in their strength. That's a good word to use in a description. The weak acids have conjugate bases that are weak. The weaker our acid, the stronger or the more favorable it is for our base to go backwards. And a lot of times we're going to be asked to compare strength by looking at K values or which way a reaction has shifted. And the first set of practice problems goes through these definitions, but also predicting the strength of our different weak versions.